Okay, so it looks like everybody in the waiting room has been admitted. So we'll go ahead and get started. Welcome everyone to the R versus Python Love Them Both workshop. We really appreciate you joining us this morning. Just a couple of housekeeping items. This meeting is being recorded, and we will be sending you a follow-up email with the links to the slides and the scripts, as well as a recording in the coming days. My name is Molly Webb. I'm a GIS programmer at the University Libraries on Danforth campus. And I'm joined by my colleague Doris Scott, who's also on the data services team with me at University Libraries, and Maze Dedukum and Marcivana from the Becker Research Computing Group. So thanks to my co-host this morning. I'm going to go out of this for just a moment. And before we get started, what I would like to have everyone do is locate the email that Maze sent you a couple of days ago, or if I could ask my colleagues to repost the links from the chat or from the email to the repl.it platform and the RStudio Cloud platform. Since we're going to be running all of our code in these cloud-based web platforms, there is going to be a few minutes of package loading when you first run the script. So I'm going to show you what is happening here with that. So you can open it up, go ahead and get it started. So then when we actually start the code portion of the presentation, we'll be good to go with that. So here on my screen right now, I've got the repl.it Python platform up. And when you run the repl.it platform, the only script that the repl.it platform knows how to run is this main.py script here. So in order to run the different scripts that are going to tackle the different content areas for today, we have the main.py script importing each of the separate scripts and telling main.py to run those scripts. So each time we change a section, we'll be uncommenting the new script and commenting out the old one so that the script that we want to run actually runs. So the lower right-hand window here is the output console window. So anything that you print out or any error messages are going to show up here. This upper right-hand window is not really of use to us during this workshop. So what I'm going to do is I'm going to hover my mouse over the middle part so I get the up-down arrows, and then I'm just going to scroll all the way up or click and drag it all the way up so that I only have this window. When you want to run your script, there's this big green run button here in the top. And so I'm going to click run. And what's going to happen is repl.it is going to go through and it's going to find all of the packages that we're importing into these various scripts. And it's going to load those packages here. Now, this could take easily 3 to 4 or 5 minutes. So that's why if you're going to be following along with us today, I'd like you to go ahead and run this now while we're talking so all those packages will be run. Another item that I would like to just point out is that in this repl.it platform, there are a couple of known error messages that are going to come up. Most notably, once the script finishes running, you're going to get a traceback error that says it cannot find the name of the script here, and that's okay. That's a known error. The script is still running fine. It just gives us a little error message to let us know that these scripts are not actual packages that it's been loaded. And so no need to worry about that error message. You can disregard it. There's a couple of other known error messages that are going to show up, and we'll address those as they come about. I think that's it with repl.it, and if any of my co-hosts can think of anything that I missed, feel free to jump in. Next, I'm going to switch over to the RStudio Cloud platform here, and we'll be looking at this in a little bit more detail. But for this, I just want to make sure that you that you're seeing the RStudio Cloud platform. You can see it looks a lot like RStudio if you were to have that application installed on your machine. And then the script we're going to be running here is down in the lower right-hand corner. It's the LDW R vs Python RMD file. This is an R Markdown file. And it will go ahead and install these packages if they're not already installed. So for this particular script, we can go ahead and just click the run button, run current chunk, and that will install those packages. We can see that R is installing those now. Okay. If you do have any questions or issues throughout the workshop, feel free to put them in the chat. Make sure that you're addressing the questions to everyone, and then either myself or one of my co-hosts will do our best to help you out there. Okay, so I'm going to bring my presentation back over here. Okay. All right, so the first couple of slides are going to address what is Python and what is R. So we're assuming that if you're sitting here in this workshop with us, that you're already fairly familiar with R and Python, or maybe one of them at least. But just to cover our bases here, Python is an object-oriented programming language. It's free and open source, meaning there's no cost associated with the actual Python scripting language, as well as most of the packages associated with Python. It's cross-platform, meaning you can use it on any operating system, and there's lots of built-in functionality within base Python that you can use. If that base functionality doesn't get you to where you need to go, then there's also a lot of third-party packages. Like I said, most of them are free, some of them aren't. That allow you to extend the functionality. And in these slides, we did provide a link to the Python package index, which is one of the main repositories of Python packages. Similar to Python, R is essentially all of these same things. Free and open source, cross-platform, lots of built-in functionality, and lots of third-party packages. And then we've given you a link to the CRAN, which is the network that has a lot of the R packages you can install to enhance the functionality of base R. And Doris is going to talk about importing data. Before we do that, I'll just let you know that we're going to do a little section of things that both R and Python can do really well. And then we're going to go into where you might want to use Python in some situations, and then you might want to use R in other situations. And then when we finish with that, then we'll dive into the code. So Doris?
Thank you, Molly. So I'm going to quickly cover importing data and just some slight differences in Python and R. As you can see, when you import the package name, you can give it like a short name. Like, so the pandas package can be referred to as PD, and the numpy package can be referred to as NP. And this is important because when you import that CSV file to call that package, you're going to use PD, not pandas, but PD dot read underscore CSV. And that's pretty much just the format of Python when it comes to importing packages or using functions of a package. And then to create an array, you create a numpy array. And so you would just do call the specific function, flights, and get that precipitation column, which is in brackets, and do 2 numpy. So you're just creating an array. On the other hand, it seems like the actual code for create. Okay, I was like, what happened to it? So just a little thing. The as should be a little a. Sorry. So when you read it in a CSV file, you can just use read.csv and just get the name of your CSV file. And when you create the data frame, it will be little a as.data.frame. And that essentially creates your information for your flight. Okay.
Okay, so another thing that R and Python both do really well is visualizing data. So when we get to the code and demos, we're going to go through data visualization in both R and Python. So just to quickly go through what we'll be covering. So in Python, we're going to look at Plotly Express, which is a free and open source package from Plotly Corporation, which you may have heard of. So there's the URL there in the slides if you're interested in additional information. And with Plotly, you can generate really nice publication quality plots. In addition, in some environments, these plots can be interactive. So we won't see that today in this platform, but if you were in Jupyter Notebook, or if you were creating plots for a web browser, you could also leverage that interactive functionality, which is really nice. And then in R, we're going to go over ggplot2. This is a wildly popular visualization package in R. It was developed by Hadley Wickham, and it's based on the Grammar of Graphics by Leland Wilkinson. ggplot2 is part of the larger Tidyverse suite of packages. So there's the URL there in the slides if you're interested in more information. And ggplot2 is great for generating publication quality plots. And as we get into the code, we'll go over how the code is structured in ggplot2 in a little bit of a unique way, following this idea of layering elements on top of one another.
Okay, so another handy tool that can be used in both R and Python is regex, which is essentially a wildcard on steroids. So if you need to search for specific, not just specific words or characters, but patterns of words and characters, regex allows you to build an expression that can find different combinations of both numbers and characters and white space. You can use regex in text editors, of course, in programming languages, which we're going to cover today. And you can also use it in databases. Another handy place that I think it would be helpful is Excel. But unfortunately, if you want to use regex in Excel, there's a separate add-in, a developer's add-in that you have to use. And so that's why I did not list Excel here on this list, because there's just a little bit more work involved. But you can use it in all of the items that I've listed here. And we'll be talking much more about regex later on.
So one thing I want to go over is which language is better for machine learning. This is just our personal opinion, not authoritative, but we believe that Python is better for machine learning just because there's more mature packages out there, such as sklearn, H2O.ai, and TensorFlow. Now there is a TensorFlow for R, and there is H2O.ai for R, but it's just that these packages are more mature on Python than R.
Okay. Also, our opinion that Python might be better if you are manipulating spatial data. So the spatial data packages we're going to be using today are open source. So You can use them in both. Well, there's R specific ones and Python specific ones. However, if you're really getting into some intense spatial data manipulation, Python has packages that link directly to the Esri suite of products. Esri is the market leader in GIS software, as well as QGIS. So if you're going to be working with spatial data and going beyond some simple steps to actually producing maps automatically, then you might want to get to know some of the Python packages associated with ArcMap and QGIS. Python also might be better for actually interacting with your machine. There's a lot of built-in packages like sys and OS that allow you to access information about your machine. What I think Python is better for is when you need to actually copy files from one place to another. Python has some really good libraries for that. And so it is my opinion that when you do need to actually interact with your machine, move files around, things like that, Python might be better for that.
Okay, so as we mentioned just a couple minutes ago, both R and Python are both great for visualization, but if you were to choose a preference, I think all of us would definitely say R would be better in that case for out-of-the-box visualization. So just within base R, there's a lot of basic graphing functionality, which is really nice if your needs are fairly simple and straightforward. And then you can obviously expand on that functionality with packages like ggplot2, which I mentioned is extremely popular. In addition, RStudio provides a really nice interface, which just makes visualization even better in R. So there's a specific plots window where you can see all of the plots you're making and click through sort of all the plots you've been making if you're trying to tweak one aspect of your plot, for example. You can also export all of your visualizations out of RStudio with point and click functionality, which is really nice. Obviously, you can do this with code or syntax as well, but RStudio adds on a lot of great benefits for beginners. The ggplot2 community is really large, so you can find a lot of help online, and there really is a comprehensive amount of documentation.
So R might be better for web mapping. Actually, the nice thing about R is that it has a package called Leaflet for R, which links to the JavaScript package, and you're able to make interactive maps with Leaflet. This functionality is not really in any Python package that I can think of. So if you do want to do web mapping, highly recommend that you use R for that. Also, when it comes to built-in documentation, kind of like what you're actually using today is this built-in documentation. R might be better for that. Python has Jupyter notebooks, but R has a lot of flexibility regarding their built-in documentation, such as R Markdown, which you can actually use R Markdown to create websites or blogs, or even like Bookdown. So if you want to create some kind of book teaching how to use R for a specific instance, you can do that.
And when it comes to the area of statistics, we think that R might be better than Python because R was designed with statistics in mind. It's no surprise that R is really good for statistical computing. There are lots of built-in functions for basic statistics, and that can be extended by add-on packages that can carry out sophisticated statistical analysis. Also, the large user community and widely available help makes it easier for users to use R for statistics. Next slide, please, Doris. Also, in the area of genomics, R might be better because of the suite of bioconductor packages that's available for genomic data analysis. So bioconductor runs in R, and it's also open source and open development, and it consists of packages and workflows and databases that can be very useful for understanding and interpreting as well as analyzing genomic data. So the large user community for R as well as for bioconductor makes it really attractive for using R for genomic data analysis. There is also BioPython, but the user community is not as large. So we have included here the URL for bioconductor in this slide. Okay, so in the next section for this workshop, we are going to do some hands-on activities, demoing the code that we've prepared, and we would use R and Python to run some basic common data analysis tasks like data exploration, data manipulation, and visualization, and we will also work on spatial data, do some web scraping, and some regex analysis. And we will do all this using the web-based platforms that Molly introduced in the beginning, the repl.it for the Python code and RStudio Cloud for our code. So thank you for joining us today. And here we have our contact information during the workshop. Continue to include questions in the chat. And if we don't get to answer your question, or if you have questions later on, feel free to reach out to any one of us. So at this point, we can move on to the demo part, or if there are questions, please include them in the chat.
Great, thanks. I'm going to stop sharing my screen now, and Doris is going to be running the code from her screen. So I'll let her bring up her screen. Again, I will go ahead and post these links in the chat for anyone who came in after we posted them. But we'll go ahead and take it away with the code. And maybe Doris, if you could just refresh our memories one more time on the whole concept of the main.py script and commenting and uncommenting.
Just unmute myself. As Molly said in the beginning, everything that you need to run is in main.py. The other code actually has like the things that's going to run. So for example, for the data exploration one, it's going to import this data exploration script. And then after that, it's going to run it. And then let's just say we're done with this section. All we're going to do is just comment this section out. And then we're going to just uncomment this section, and then just run that code. And as you can see, you're going to get some kind of error. Please just ignore that. So I'm just going to comment this again, since we are actually on the data exploration part. And I already ran it, but I'll run it again. So also make sure when you do uncomment things, that everything's properly indented. So as you can see, it's giving me an error message, but that's fine. So I'm good. I'm ready to go.
Okay, thank you, Doris. So this demo part, we are starting off with Python, and we are going to start off by importing the data that we're going to use for this first part, looking at data exploration and data manipulation. We are using the pandas package as described on the slides, and we start off by importing pandas as PD. And then we have the line 7 where we're referencing the files. We have the input file reference and the output file reference. In line 11, we read in the data using the read_CSV in pandas. So we say data, that's the object name we are giving to our data, and equal to pd.read_CSV, and then now we use our input data file reference. So when the data is imported, we can now go ahead and print it if we want to, and we can now do the other data exploration parts. So on line 20, we are using the data.describe. Oh, sorry, I skipped over the functions where we are exploring the data. We are using the type function to look at the structure of the data. Did we run that, Doris?
Yeah, so it's going to be up towards the top of the output there.
Okay.
See it up there,
I see. Yeah, I see that.
Let me just expand it.
Oh,
there we
I
go.
see it
Thanks,
now.
Doris.
Thank you, Doris and Molly. The output for a print type data shows we have a structure where the data is 50 by 5, so 50 rows and 5 columns. And then we did the data.shape function for our data, and we to see yeah, so, sorry about that. The type was going to show us that is the pandas core frame data frame type of data, and then the shape gives us the dimensions, which is the 50 rows and 5 columns. Sorry about that. And then we have the data.head just to print out the first few rows of our data, and the data.tail, which prints out the last few rows of our data. We also use this the data.describe function. So our data frame name, data.describe, and the argument here, we want to include all the columns of the data, and the output, as you can see, thanks Doris for highlighting it. It returns a summary statistics for the data frame. And on line 22, we are just printing out the data frame to print out the whole output displayed on the screen. And the next section in line 24, this is where we're doing some data manipulation. And we are trying now to add a new column to our existing data. So we want to add a column called BMI. And we are wanting to use data from columns that are already existing in our data frame. We want to use the weight and the height column to do this BMI calculation. And so the code here, we start off with the data frame name, which is data. In square brackets, we include the new column name BMI equal to the round function will round the output to 1 decimal place. And so we're using that formula 703 times the weight value and divided by the height value squared for our BMI calculation. The output, we can see the new column is generated.
Yeah.
Do we have the output?
I can't really.
You would need to print that out to see that on the screen.
Okay.
Okay, so you need to run line 25 to see that on the screen, to see the new column BMI.
Yeah. Line 25 would need to read print, open
Okay.
paren, data, close paren.
Yeah.
There we go.
Thank you, Molly.
Sure thing.
There we go.
Okay.
Right here.
There it is.
Excellent. So we can see the new BMI column that's been generated, and the output is the values are rounded to 1 decimal place. In line 31, we are now subsetting. And so we want to subset based on variable values. So we want to look at only data for people who are taller than or equal to 72 inches. And we start off with our object name tail underscore data equal to, and then we use this data.lock function, and we use the data frame name, and then the square brackets we have the height in inches, and the greater than or equal to comparison operator and 72, so we can be able to subset all the rows for data for people who are 72 inches or tall or more than 72 inches tall. And then we can print that too by doing print tall data, and we can see the subset what we have generated. And similarly, in line 34 we're doing a similar subsetting, but now we are trying to get data for those who exercise daily, still using the data.log. Okay, and on line 38, we are now subsetting non-contiguous columns, and we are still using the data.lock method and using the indexing. So we use that data.lock and individual column names in quotes. And notice that we are leaving where we just want all the data for those columns, those individual non-contiguous columns. And we call it narrow underscore data. And now that we have it, if we want to export our data out of this platform, we can use the code on line number 43. And we say narrow underscore data and send it to underscore CSV. And in this case, we are saying indexing equals to false. So that gets rid of the indexing column, that sort column. So this is pretty much, yes.
Oh, I was just going to ask Doris if she could go just a few files down in the data folder and click on narrow data. It's just a little bit under your mouse. There you go. And
Yeah,
so this is what that export looks like as a CSV.
Thank you, Molly. I was looking for it. I was like, where is it?
No problem.
Thank you both. Yeah. Okay. So now we have our narrow data exported, and we've seen the data exploration and data manipulation in Python. We can move on to data visualization. I thought we were doing all of, oh, sorry. Are we going to do the RStudio?
Yeah, we'll go ahead and do the R section too, Maze. Thanks.
Okay, so in RStudio, you will notice that the Markdown document has a lot of text beginning. At the top, we're just explaining and describing what we are doing and listing the packages that will be used during this session and during this workshop. And then we, in the beginning, Molly showed how you could just run chunks of code to load the packages and run chunks of code during the different exercises. So we are moving down to line number 63, where we are importing data. So there are a variety of ways you can import data in R, but we are going to use the read.csv function, which is one of the read table functions available in R. The way we are doing this in line number 73, we are reading in our data. We're using read.csv function within the parentheses. Notice that we're using the here package. And this is a really nice package that can allow us to define a specific folder and reference files in that folder without needing to deal with paths. So we have a folder called data with uppercase D. That's where our file for import is located. And now we are referencing using the here function and the file name in the code. So if we run that, we import the data, and this is the same data that we use for the Python activity. So our data is imported, and we also assign it a name called data. So that's our object that we will be creating here as well. And then we will use that data object for our data exploration activity. So line number 92 creates the data object. So the few functions here for exploring the data object, which is a data frame, we have a dimension or dim function, which gives us the dimensions. In Python, we use the shape function. And then notice here in R, there's also a head and tail function that returns the first few rows and the last few rows of data. And then the summary function, which generates a basic summary statistics for the columns of the data. So that's line number 98. And in line 99, we are just printing out the data again. And in line 100, we have this view function, which helps you view your data in a spreadsheet-like format. And if it's a large data set, there's a nice scroll bar. You can scroll up and down. So this is a nice functionality in R for large data sets. Okay, the section for data manipulation is we're doing the same code, the same task as we did for the Python. So we are now adding a new column. So in R, we are using the data frame name, the $ operator to add the new column BMI. And we also have the round function. We're setting the output to 1 decimal place. So notice that we are using here the data frame and the $ operator to extract the weight column values and the $ operator to extract the height column values. And the output is exactly the same as we saw for the Python output. And then for the subsetting, we are also using square brackets. And in the first example here, we are looking for rows of data for those who are equal to or taller than 72 inches. We have the row index, comma, and then the column index is blank. And similarly for line number 112, where we are subsetting data for those who exercise daily. And then we subset for non-contiguous elements, still using squared brackets, and we leave the row index blank, and we use this C or combine function. And within the parentheses, we indicate the individual column names in quotes. So now we have generated our narrow underscore data, which has 3 columns. And we want to export that out of R. So that will be the code on line number 122. Notice we use this write.csv function. We are exporting the narrow underscore data object, and we are wanting it to go to this location of data, uppercase D, using that here function so that it references to that specific location without us worrying about the path. And the argument row.names equal to false, we include it so we can get rid of that indexing column. And if you go to the files pane of our studio, you will notice the narrow underscore data.csv file is there. So this is where we end with data exploration and data manipulation. And thanks very much, Doris and Molly.
No problem.
No problem.
Yeah.
Great. Thanks, Mazi. So now we're going to move back to Python, and we're going to jump into the data visualization section. In Python, go over Plotly Express. And then after we go through the visualization in Python, we'll jump back over to our studio and take a look at ggplot2. So we've got those lines uncommented. So Doris, if you wouldn't mind hopping over to the data visualization script. Awesome, thank you. So we're going to use the same data set that Mazi was just working with, and we're going to use the same data frame object that she created called data in the most descriptive fashion. So again, just that code is included there. So we're going to import pandas and then continue to refer to that as PD. And then, as I mentioned when we were going through the slides, we're going to go through Plotly Express. So in that case, we want to import that as well, and we will refer to that as PX. So you can see the import of those in lines 4 and 5. And then again, in line 8, you'll just see the reference to the data file we're going to use and how to read that in as a CSV in line 16. Again, that's just a repeat of what we just did with Mazi. So we're going to cover some popular visualizations on the fairly basic end, but just to demonstrate how you can pretty simply generate really nice visualizations to show your data. So for histogram in Plotly Express, you're going to use a histogram function. So in line 20, we'll see the beginning of that code. And so you're going to call that function by using px, which is again how we're referring to Plotly Express, dot histogram. And then within those parentheses, the first thing we need to specify is the data we're plotting. So the data frame will be specified first, and that again is named data. And then we've got a comma, and then because in a histogram, we're basically just looking at the distribution of a single continuous variable, we just need to specify one variable here, and we're going to specify that we're going to use weight in pounds as our variable here. So in the parentheses, we're going to next say x equals weight in pounds. And then if we want to add a color, we're going to add that on with the color underscore discrete underscore sequence argument, and we're just going to use violet. And then we're going to add another optional argument for n bins, which is basically just the number of bins we're going to see in our histogram, and we're going to set that to 15. You can leave that argument out, and Plotly Express will choose a number of bins for you. And just for some aesthetics, we're going to set a title and some labels. So we're going to change our label for the x-axis from the column header, which is weight underscore pounds, to a nicer looking title where the W is capitalized in weight and pounds is in parentheses. And then we're going to write that as an image. So we're going to use, so we've set that histogram equal to hist, as you see at the beginning of the code in line 20. So now we're going to say hist.writeImage to write that out. And in parentheses, we're basically going to say where we want that to go. So if you, Doris, if you wouldn't mind scrolling up just a little bit for a second in the script to see those output. Yeah. So the references you'll see for each of the plots are in lines 10 through 13. And so you'll see those are just going into the figures folder, which we can then refer back to over here on the leftmost pane. So thank you, Doris. So Doris has just clicked on the visualization we wrote to hist.png, and you can see that's a really nice histogram looking at the distribution of weight in pounds. Cool. So now we'll go back to the data visualization code and jump down to scatter plots. So we'll go down to line 26. So the function for scatter plots in Plotly Express is scatter. So we're going to call that with px.scatter. And then inside the parentheses, we're going to have a similar mix of components. So first we're going to specify the data frame again, which we do with just data, as that's what we named it when we read it in. And then now obviously a scatter plot is going to look at an X and a Y variable. So here for X, we're going to look at height, and we're going to plot weight on the Y axis. We're going to give that a nice title, and we're going to make the labels on the X and Y axis look a little nicer with our specifications there. And just to add a little more detail than what I did with the histogram, when you do specify the labels, you'll see those are specified using a colon. So you first specify what the column name is, and then colon what you want it to look like in its nicer form. And then again, we're going to add a color with color discrete sequence again here with red. And so before we go over to actually look at that scatter plot, we're going to also make a second scatter plot to add another parameter into this plot. And this one we're going to call scatter underscore diet. So we're going to basically use the same variables. We're going to continue to plot height in inches on the x-axis and weight in pounds on the y-axis, and keep those nicer axis labels. But here we're going to add in another parameter, and that's color. And we're going to set, instead of setting the color just to red as we did in the scatter plot, the initial scatter plot we made, we're now going to add in another variable as color, and we're going to use diet in this case. So then with this last argument here in this scatter underscore diet code, we're going to tell Plotly Express what colors we want to use for those two diet values. So if you remember from the data we read in, the diet variable has two values, either healthy or unhealthy. And so we want to specify exactly what those colors should be. And so we specify those now with the color discrete sequence, and then we put those colors within the square bracket separating by a comma. So what's going to happen in Plotly Express is the color we specify first will be assigned to the variable value that appears first in the data as you look at it or print it out. So Doris, if you wouldn't mind hopping back over to the figures. Yeah, and so here first is our basic scatter plot where we see all the points are just red, and that looks really nice if that's what you're looking for. And then if you click over to the scatter diet, awesome, thank you. You can see now the plots are colored based on whether that row in your data set has a value of healthy or unhealthy in the diet column. Unhealthy appears first in the data set in the diet column, so that is set to brown, and healthy is set as blue. Cool. So we'll go back over to the data visualization script for one more visualization. We're just going to look at a box and whisker plot. And for that in Plotly Express, the function is box. So again, we're going to refer to it as px.box. And then we are going to, as we have before, yes, thanks Doris, we're down in line 38 now in the script. We're going to refer to the data frame first, which is data, and then our X and Y variables. So here we're going to, our X axis is going to be a categorical variable. So we've got exercise, which has 3 values. And then on our Y axis, we're going to have that continuous variable, which we're going to use weight in pounds. And then we're going to add a title, parameter, and labels again to make those X and Y axes look a little nicer. And we're going to add a color of purple. Lastly, we've also added in an optional argument here, points equals all. So you can leave that out and you'll have a very nice looking box and whisker plot. If you want to add in the actual points as well to add on that, that's how you would do it with points equals all. And then again, as with the other plots, we'll write that to a file in line with the code in line 41. And then we can jump back to the figures and the box. Yeah, thank you. And then there we have a nice box and whisker plot. So that's pretty much it for Plotly Express. I would just say with Python, there are lots of different packages or libraries that people use for visualization. So, and I think there's lots of them that work well. It doesn't, it's not the same, I think, environment as around R, where there's just so much focus on ggplot2. Okay, so now jumping over to R, our Studio Cloud, we're going to take a look at ggplot2. So as I mentioned several times now, this is a really popular package. And one thing to point out here is it's really based on this idea of layering of elements. So all of the plots you make in ggplot2 will sort of have at their center code specified in the ggplot function. That's sort of the starting point. And within that function, you specify the data frame you're going to use. And sorry, I should back up for just a second and say, again, just like with Python and RStudio, we're using that same file that Mozzie read in, and we're using that same data frame. So that code is just a repeat of what Mozzie did. And so we're going to use that data frame that's called data. And so in the ggplot function, first we're going to specify the data, which is also referred to as the data layer. Again, in this idea of layering elements to make plots in ggplot2. So awesome, thank you, Doris. So you see there in line 129. So the first thing we specify in the ggplot function, again, is the data frame, which we've called data. And then within the ggplot function, there's actually another function called AES, or the aesthetic function, which is also the aesthetic layer. So that's sort of the second layer you'll hear about with ggplot2. And within that, you're going to specify the exact variables within your data frame that you want to plot. So here in this basic histogram example, we're going to start with histograms here in RStudio like we did with Python. We're going to start with just one variable because we're just plotting the distribution of a single continuous variable in this histogram. So we're going to say X equals weight in pounds because that's the variable we're going to use. And so that's the extent of our aesthetic layer for this graph. So the last main layer you'll hear about in ggplot2 is the geom layer, or the geometric layer. And that is where in ggplot2 you specify what type of plot you want to make. So, and that is added on with a plus sign after the ggplot function. So you'll see here again, still in line 129, that we've closed the parentheses on the AES function and the ggplot function, and we've added a plus sign, and now we're saying we want to add on geom underscore histogram, which is the function to generate a histogram. So then some of the arguments we'll add there are all optional. So you could leave those parentheses completely empty, but we're going to add on a color, which we're going to say is blue. And in a histogram in RStudio, that's going to color the lines of the histogram. And so if we want the bars to be filled, we're going to add a fill color. So we're going to set that equal to violet. And again, we're going to add in an optional bins argument, which you can also leave out, and RStudio will fill that in for you. But we're going to do that here, and we're going to set it to 10. Similar to what you saw in Python and Plotly Express, we're going to add on one more function here in RStudio that's called labs. So again, that's basically all of the labels, and that's going to allow us to add in arguments for title and X, and Y to add in a nicer title nicer X and Y axis. So you'll see that there. And then when Doris runs that in our Markdown document, you'll actually see the plot right below, right below the code. So that's a really, nice looking plot. From there, we're going to skip down to scatter plots. I'm going to go through sort of all these 3 iterations of a scatter plot together. So starting in line 137, then the next plot in 140, and the next plot in 143. And I'm just going to sort of let you know sort of how this plot is becoming more complex and the parameters that are being added on. So again, in line 137, we're going to start with the ggplot function. That's always where we start. And the first thing we're going to specify is the data frame, which is called data. Then also within that ggplot function, we're going to add in the aesthetic function. Here for a scatter plot, we have both an X and Y variables. So we're going to add that in with height and weight. And then we're going to close that AES function and the ggplot function. Then we're going to add on the function for scatter plots, which in ggplot2 is geom_point. So you've got that specified at the end of line 137, and then in line 138, we're going to add on some nicer labels for the X and Y axis, and we're going to add on a title. Starting in line 140, we're going to add a couple of additional things onto the scatter plot. So if you noticed in line 137, we left the geom_point function empty. There wasn't anything in the parentheses, and that's fine. That'll generate a default scatter plot, which will look very nice. But say we want to change the point size or the point character or shape or something like that. So here we're going to change the size. So we're going to add a size parameter in there and set it equal to 2. And we're also going to add a color. So we're going to set that as red. Lastly, down in the code, starting in line 143, we're going to add one more parameter onto that graph, and that's going to be adding in a whole nother variable into the plot by using color, just as we did with Python. So we're going to start with the ggplot function in line 143 as before and set the data frame as data. We're going to add in height and weight as our X and Y variables in the AES function. And then also in that function, we're going to say color equals diet. So we're telling ggplot2 that we want to add in the diet variable and we want to use that as color. So then we're going to continue on with the scatter plot. So we have geom plus geom_point added on to that, and we're keeping the size argument, but we've removed the color there. And then now, similar to what we did with Plotly Express, we're going to tell RStudio exactly what colors we want to use for our 2 values of diet, unhealthy and healthy. So RStudio treats this a little differently. So you'll see here with Scale Color Manual, we're going to supply the color values as a vector. So values equal C, and then in parentheses, we're specifying the colors. So in RStudio here, the color that's specified first is assigned to the variable value that comes first in the alphabet. So it's a little bit different. In Plotly Expressed, it assigned the first color to the variable value that appears first in the data, but in RStudio, it's an alphabetical order thing. And so then lastly, with the labs function, we're going to add in some nice X and Y axis labels and a title. So here, if you, oh, awesome. Thanks, Doris. So now you can see the code has been run and all these plots are visible within the R Markdown document. We have the first scatter plot that's just black, the second one that's red, and the points are a little larger. And lastly, the plot where the diet has been added as a third variable, and that is specified as color. And then just as in Plotly Express, RStudio also automatically creates a nice legend for those colors. So actually, before we jump down to the box and whisker plot, Doris, would you mind running a couple of those scatter plots, copying and pasting that code into the console so we can also take a look at the plots window? Awesome, thank you. Okay, so let me just point out this plots window as we finish out the scatter plot section. So this is a really nice area to take a look at your plots in RStudio if you're not working within an R Markdown document. And the nice thing about this here is it gives you a nice window to visualize your plots. You'll see at the top left of that plots window, there are a couple of arrows. So right now the right facing arrow is blue. So if you click on that, Doris, if you wouldn't mind going over to the plots window and clicking on, yeah, that arrow, thank you. You can use those two arrows to scroll through all of the plots you've made. So if you're playing around with maybe the point size or character on your scatter plot or some variations on your title or whatever, and you want to keep looking to see which visualization you like best, you can scroll through them, and I find that to be really nice. In addition, in that plots window, Doris, if you move over to the right a little bit, there's an export drop-down menu, which is also really handy. Again, another nice function of RStudio for newer users. You can save your visualizations as an image, and if you click on Save as Image, you'll see that you get if you click on the image format option there in the window, in that Save Plot as Image window, where it says PNG.
I already did that, but it's not showing up. So I'm trying to find it.
No problem. Okay. Anyway, there's a drop down. That's okay. It's not a big deal. When you open that window, you'll see there's a drop down menu where you can choose from the image format. And so you can choose JPEG or TIFF or PNG or whatever and export as any of those. Also, you can export as a PDF. So that's really handy. So lastly, just really quickly, I'm going to show a very basic box plot in RStudio. There are some additional plots in this section too that we're not going to go over just for time. They're a little bit of an add-on to more than we saw in Python. So I'll just let you look through those on your own. And those are dot plots and violin plots. But to end, we're just going to make the box and whisker plot that's a little bit, let's see. Okay, yeah, sorry. So in line 149, we're just going to make this basic box and whisker plot. So, you know, very simply, you're just going to use the ggplot function again, specify your data frame. Within the AES function, you're going to specify your X and Y variables. The geom function you're going to use is geom_boxplot. We're going to set the color equal to blue, and then we're going to add some nice labels. So that's really the extent of it. What we wanted to go through today. And we tend to have a tough time getting through all of the content in the workshop because we have so much great stuff to show you. So I'm just going to leave it at that. So hopefully that was helpful, and let us know if you have any questions. Thank you, Doris.
Okay. Yes, thanks for that. And thanks, Doris, for switching us back over to the Python window. And you can see that Doris is commenting the DataViz script and then uncommenting the spatial data Python script, so we can take a look at that. Okay, so Doris, if I could ask you to click onto the spatial data Python file, I'll go ahead and get started walking through that. It looks like it's going to install a few more packages here, so we'll just, if it feels like it needs to do that, we'll go ahead and just let it do that. Okay, so working with spatial data, there's a couple of Python packages that are helpful for this. And like I mentioned at the outset of the presentation, the ones we're using here are open source libraries, but there are some third-party libraries that come with licensing that you can also use if you're working specifically with, say, Esri products. And feel free to touch base with me if you have any questions about those. We're going to import the GeoPandas package. As the name suggests, it kind of tacks on to the pandas package that we looked at before. So you can see in line 6, we're bringing in GeoPandas, and then line 8, we're bringing in pandas as well. Descartes is going to help us out with some mapping and visualization, and then the matplotlib function is going to help us produce our plots. Lines 15 through 17, what we're doing is we're just referencing those external files. So I've dropped into the data folder 2 shape files. And Doris, could I ask you to just expand the data folder? I just want to make sure that I point out that when we're talking about a shape file, we're not talking about one specific file. I'm sure that will open up once the packages get done installing. We're not talking about one file, but shape files are actually a group of about 5 to 7 different files that all make up different aspects of the spatial data file. When you're working with spatial data, you essentially have 2 components. You've got the shapes or the geometries. That's what we're actually seeing on the map. And then you've got a table that's behind the scenes giving us information about each one of the shapes in the spatial data file. So if you expand the data folder and those files pop up, which they will eventually, you'll see that, for example, Mo Counties 2018 is not just one .shp file, but it's several. Same thing with Metro STL. So Missouri Counties, of course, is just a shape file that shows all the counties in Missouri. And then Metro STL is a single polygon that represents the border of the St. Louis metropolitan area. All of our visualizations that we're producing today are going to be showing up in the figures folder, and I've just started a little path to all my figures are going to be called Missouri, and then we'll append a number to them, figure 1, figure 2, figure 3, so on and so forth, so we can see the different figures there. Okay, so then the next section, lines 21 and 22, is where we're going to be specifying the coordinate reference system for the spatial data. Essentially, we need to pick appropriate coordinate reference systems for the data, because when you take something that's spherical, namely the planet, the Earth, and you take locations that are specified on the round planet, and then you spread them out, you kind of flatten them out onto a screen or a paper map or whatever, you're going to get distortion of your shapes and your locations. Each coordinate system, and there's like thousands upon thousands of them, is designed to minimize distortion for a certain area. So when we're bringing in the locations and we're starting with them fresh, we're going to be working in the world CRS variable. That is a geographic coordinate system that represents locations on the Earth on a sphere. When we flatten them out, we want to make sure that we're using a coordinate reference system that's appropriate for our area, namely Missouri. And so we're going to be using one of the Universal Transverse Mercator, or UTM coordinate systems. Zone 15 North is the area that covers Missouri, and so we are referencing that particular coordinate system. Each of these coordinate systems we're referencing with their specific EPSG codes. Every single coordinate system has this unique code, and so our library knows that when we reference that particular code, then that is the projection that we want. Now, I could easily probably talk for 5 hours about coordinate systems and projections, so if you have any questions about those, I invite you to definitely reach out to me offline, and we can talk about them for a really long time if you want. But for now, I'll just kind of leave it at that you do need to have an appropriate coordinate system for your data, or else your locations are not going to line up properly. And that's the whole idea behind GIS, is taking different layers of data and stacking them on top of each other. Okay, so in line 25, we're actually reading in that shape file. It's going to be set to a variable called counties. And then in my code here, I'm printing out some various information about the shape file. So now it looks like our packages have finished installing. So Doris, could I ask you to hit run one more time, please? Thanks. And so hopefully it will do its thing. Okay, maybe it's going to install some stuff, no big deal. But essentially what we're going to do is we're printing out information about this shapefile. So I want to know, okay, what is the data type that shapefile is coming in as? And it's going to be coming in as a geodata frame. So similar to Python or similar to Pandas, Pandas brings in data frames. This is similar, only it's a geodata frame, meaning it has got that spatial information along with it. And the coordinate reference system we'll see from the start is going to be the WGS 1984 or that EPSG 4326 coordinate system. But then in line 37, we're going to run the toCRS function within the GeoPandas library, which is going to convert that EPSG 4326 coordinate system into that UTM coordinate system, which is appropriate for the area of Missouri. So in lines 39 through 43, we'll print out that information again, and it will show us that the new coordinate system is the UTM 15N north coordinate system. Okay, and so then once all that stuff is printed out, we know that we're working with the right coordinate system here. Then we can make our plot. So in lines 49 and so let's start with line 49. I'm making this plot called counties base, and I'm starting it with the UTM 15N counties file that we created, and I'm using the plot function within matplotlib, and I'm just specifying give me white shapes with a black border. And then to save the figure, we'll just use the save fig, and you can see I've appended underscore 01.jpg to give us that first plot. And so hopefully that's created. So maybe Doris, can we take a peek in the figures folder and see if that is there already? Okay, so that's not there already. No problem. We'll just wait for that to come up, and I'll continue on explaining through the code while those packages are loading yet again. Always kind of fun to see how this platform functions. Okay. So then after we've done our basic plot, then we're going to start to do just a little bit of some analysis steps. One thing that's pretty common when you're working with spatial data, especially polygons like county boundaries, is to create centroids, right in the middle of the polygon. So GeoPandas has a really handy centroid function that's associated with the spatial geodata frame. It's just taking that geodata frame and using .centroid, and that gives you points that are centroids of those polygons. So those centroids are going to be another geodata frame, and they're going to take on the same coordinate reference system as the county's UTM 15N file that we saved before. So then in lines 67, we're going to add those centroids to our existing plot. So you can see we've got the parameter AX, and so that means take that existing county's base and add these centroids to the top. So just like Marcy was explaining how with certain visualizations you're essentially just layering things on top of each other, it's the same kind of concept here. We're just layering spatial data onto existing plots. So I've set these to be black dots that are going to have a white border, and now we can see my my information that I printed out is coming in, and in our figures folder now we can see those plots coming in too. So in line 68 we're saving Missouri underscore 02, so we can see what this looks like. So Doris, could I ask you to click on Missouri 01 first? Okay, so there's our basic map of just Missouri counties, and then Missouri underscore 02 is going to be that figure with the centroids applied to it. Thanks a lot, Doris. We can go back to the script. Thanks. Okay, so we printed out those, so now we're down there at line 73 now. Okay, so another really common operation when you're working with spatial data is buffering. So essentially just creating a new set of polygons that represents an area around either points or polygons or lines. In this case, we're going to be buffering our centroids, and we're setting the buffer distance, so that's going to be the radius of the buffer, at 16,000. So the reason why I've set 16,000 is because the buffer is going to be, the buffer distance, the unit of the buffer distance is going to be associated with the linear unit associated with the coordinate system. So going back to everything's based on the coordinate system. So the coordinate system, the linear unit associated with UTM is meters. Every single coordinate system has a specific linear unit associated with it. Most of the time it's meters or feet. So with UTM coordinate systems, the linear unit is meters. So any kind of distancing that we're setting, we need to set it in meters. I wanted to do a buffer of about 10 miles on these centroids. And so 10 miles is just a little bit under, or it's just a little bit over 16,000 meters. So I just rounded down a little bit. When we create that buffer, it's also going to be a geodata frame, and the coordinate system is going to be the same coordinate system as the input data or the centroids. So you can see, Doris, if you could scroll just up a little bit in the output window. Okay, you can stop. Okay, scroll down a little bit more. Scroll down. It says the data type of the buffer polygons is a geoseries, which is essentially just a slice of a geodata frame. I misspoke before. And the coordinate system is the UTM coordinate system. All right, so now that we have our buffers created in line 86, we're going to again add those buffers to the plot. I can change my colors if I want using the face color and the edge color parameters, and then I want to make sure that I add those to the base. So that is going to show up as Missouri 03. Doris, if I could ask you to expand the figures folder and show us Missouri 03. Thanks. Okay, so now we can see we've got a really light buffer polygon around those centroids, and I set the alpha value, which gives us a little bit of a transparency. They had about a 50% transparency. So there is our buffers. Okay. All right, and so next, what we're going to do, if you could scroll down a little bit for me, Doris, is we're going to perform a spatial selection. So this is another really common operation in GIS where you're going to be selecting certain features based on their relationship to other features. In this case, we're going to be selecting centroids that are within our metro area. So the first thing we do, we bring in that metro area shapefile and we convert the coordinate system to UTM 15 north like we did before. And then down in line 107 and 108, we're going to I'll go through the rest and then we'll see what these visualizations look like, but we're going to add that to the our base visualization, giving it kind of an orange color with a red outline. And then, well, actually, Doris, would you mind clicking on Missouri 04 just since we have it open right there? Awesome, thanks. So we can see now we've got our metro area overlaid our counties, and it's got an orange fill with the red border indicating that that's our metro area. Thanks, Doris. You can go back to the script. Okay. And then let's see, I think we're down around line 100 something. Okay, there we go. So in line 107 and 108, we added that to our plot. Okay, So now to actually perform our spatial selection, we need to isolate that metro polygon, because remember what I said before, spatial data is made up of two parts. It's made up of the geometries or the shapes and then the associated data for every feature. So what we want to do is we want to isolate those shapes so we can use that to run our spatial selection. So that is happening in line 111. We're using the geometry function, and then we're saying, okay, take all of the geometries, which in this case is only one. We only have one polygon. And so we're saying, okay, take the first geometry in that shape file. And then we, in line 114, we're using the within function to create a new series that are the centroids that are within that metro polygon. So that's going to give us a new spatial data set that is only those centroids within the metro area. And so going down to line 124, we're going to add those centroids within the metro area to our plot. We're going to give them a red color so they really stand out. And then in line 125 is when we save out our plot. So Doris, figure 5, please. Thank you. So now we have our metro area with those red centroids called out there, all the centroids that are within the metro area. All right, so in this script, we read some spatial data. We did a centroid operation, we did a buffering operation, and then we did a spatial selection. And those are all really, really common operations that you would do when you begin working with spatial data. So now we're going to flip over to the RStudio Cloud side, and I'm going to show you essentially how to perform these same operations in R. So we're down at line 167 is where this begins. And we've already installed the packages. Now for this particular, for R, we're not using GeoPandas in this case. We're using the package rgeos and rgoodle. These perform a lot of the same functions that our GeoPandas function did for us in Python. So in line 175, what we're doing is we're reading in the data using the read OGR function. And I just want to point out that for the DSN parameter, the DSN parameter stands for data store name. And so that is wanting to know the location of where we have this spatial data saved. And so in this case, we have it saved in a folder called data, and the shapefile name is Mo Counties. All right, so yep, there we go. We've got Mo Counties, and then within that folder, we've got the Mo Counties shapefile, and so that's what we're using for the layer parameter. So DSN is the location, and then the actual layer name is the layer parameter. We're going to plot these plot the counties in gray as soon as our packages get done loading. It looks like we're installing rgoodle there. That's totally cool. Oh, it's loading everything. Nice. Well,
I don't know why.
That's okay. No big deal. I'll just continue on, and then those plots are going to show up whenever they're ready. Okay, so the in terms of doing the centroids and the buffers, the workflow is pretty similar. Only in this case, in line 87, we're going to be using the gcentroid function. All right, and so for the parameters for this, we want to say, okay, we run the centroids on the counties file. And then the by ID parameter is important because what that means is for every feature, I want you to create centroids for every feature. If we eliminated that by ID parameter, then it would just create one centroid at the middle of our data set, which is Missouri. So there'd be one point right in the middle of Missouri, which is not really super helpful. Okay, let's see. Have our plots shown up yet, Doris? Are they showing up at the bottom?
Let me just do it.
Sure.
There we go. If you can
Cool,
see it.
thanks. Awesome. So here you can see our Missouri counties. And then if we run the chunk right below that, then we should see those centroids show up on our plot. Yeah, right there, Doris. Awesome, thanks. All right, so there's our centroids. Okay, so now if you could scroll down a little bit, now we're going to do our buffers. So again, we've got the buffer specified in meters here, 16,000 meters for an approximate 10-mile buffer using the gbuffer function. For gbuffer, we need to give it a spatial geometry, which is our centroids, and then of course the width, which is the radius of the buffer. Then in line, we're going to build this on top. So first we're plotting the counties, then we're plotting the centroids, and then in line 208, we're plotting the buffers with the color cyan fill, and the add equals true says add this to the existing plot. So now we can see that cyan buffer showing up on our counties plot. Okay, and then next up, we're gonna bring in our metro polygon and do our spatial selection. So again, line 214, we're using that same read OGR function. We're getting our buffers in there. We're plotting counties, centroids, buffer, and then we'll add that metro outline using kind of a red color that's specified by RGB values there. Okay, so we can see that red polygon, which is our metro. And then let's see, Doris, could you scroll up a little bit? It looks like, I guess those gray polygons just look gray because of the red on top of the cyan. So that's fine, no big deal. For some reason I thought, oh, maybe I made a mistake, but no, it's just the red is making the cyan look gray there. And then if you scroll down one more chunk, then we'll do the spatial selection. Okay, so line 228 through 233 is kind of a repeat of what we did before. And then lines 236 is where we're actually running that spatial selection. So we know just from working with regular R that often we will subset records using those square brackets. It's the same thing for the spatial selection too. We're going to set a variable called metrocentroids, and it's going to take the centroids and it's going to subset them by everything within the metro polygon. So that's the syntax of that. And then finally, we'll add those metrocentroids to the plot, coloring them in kind of red squares with a black outline there. And I think that is it for our spatial section. So thanks a lot, Doris. And now we'll go on, we'll switch gears a little bit and we'll take a look at the web scraping.
Okay, let me just comment this out. And I'm just going to uncomment import web scraping. And I'm just going to run it. So let me just get to the web scraping. So the package that that's used for web scraping in Python is called Beautiful Soup. So just to give a quick overview of what these two are doing, line 4 and 5, you're just importing the this package called request, so you can make the calls to your websites. And then you're going to import Beautiful Soup from BS4, so you can actually extract that data from HTML and XML. And then we're just going to save our output to data to the data folder and call it website_text. So if you actually put this in your folder, in your web browser, as you can see, it's just a very simple page. So just want to keep it simple so you can, just for those who have not done web scraping before. So right here, we're just giving, we're getting the request to get that website address. and to get that text. And so then you're just going to parse your text out. So I'm just going to run this part. And it's going to, let's see if I can find it in the data. Trying to see.
Are you looking for website text, Doris?
Yeah, I see. I'm sorry. I was little just gonna go up here. I think so if you see in this I don't know why I did it like 3 times, but whatever. So here's all the website text, and as you can see, there's the tags and all of that. Wait, yeah. And
Doris, just a suggestion. If you click the little X arrow in the top of the, that will clear your output. And then if you run it again, it will only have the output for the web scraping.
Okay. Yeah,
that
apologize.
might make things a little easier. There you go. So now you can scroll up to the top.
Okay.
It can get really confusing.
Yeah. Yeah, as you can see, this is all of the text, and for some reason it's just doing all of it. So here's the results. Actually, that's from line 17 to 21, and it's just doing the parsing, and you can use the print soup.printify for that. And as you can see, there's the text. And then the next thing is to show the TD tags. So if you just want to do that, you do soup.find_r all TD. So it's just finding all of those tags. And as you can see, you see the tags and then also what's in those TD tags, I believe. Yeah. So then let's just say you want to find a list of links. So you always, like when you're using find all, you need to know the actual name of the tag. So if you're not familiar with HTML, I highly recommend just putting a Google search for W3 schools, and they have a lot of information about HTML. So for the HTML tag for link is A. So as you can see in soup.find_all A, print the links. So that's what that did. It's not that many links just because it's a very simple page. And now we want to get the actual text that's associated with that link. And as you can see here, you have lesson 2 and then the back to WWS index. And then you can actually save your, where am I at now? Oh, and then after that, you can get the list of URLs. So like if you just want the actual like page names, if you can see that here, you can do that. And the list of URLs is from 49 to 55. So again, you're just printing that list, finding everything with the A tag, getting the actual name of the HTML page. And then finally, you can save your text into a file if you want to do some more scraping. And we saved it in the data folder. And it's called, I think it's website text. No. Oh.
Yeah, that's it, Doris. Website
okay.
text.
Sorry, everyone. So this is the actual text file for your website text. So that's how you do it. That's a brief explanation on how to do it in web scraping in Python. So now I'm going to go over how to do it in R. So there's a package called rvest that allows you to do that. And one thing that you can do with our packages that are within, I'm losing my train of thought. But one thing that you can do with functions in R is to use this nifty pipe operator, which moves operations from one function to another. So to paraphrase this code, it's saying, and create a variable called web page, and you can also use arrow as opposed to equal signs. Use this function in Arvis called read HTML, tag get this site, get the TD tags, and then show me the text for that. So like the advantage of this is that you're not writing it over and over and over again. You can just put the pipe in and just pass it along. And as you can see, the web page values are here. So if I just type that in, you can see all of the web page text here. And that was extremely brief. So now Molly is going to show you how to use some regular expressions with this website. So do you just want to do it from here and then we go to Python?
Sure, yeah, let's change things up a little bit since we're here. So Doris got us started actually grabbing the HTML and parsing it out a little bit from the web page. Now that we have that text saved in memory here in RStudio, we're going to use regex to kind of clean it up a little bit. So when we look at the web page variable printed out there in the console, we can see that we have a lot of these /n's. And what that means is it means a carriage return. It's just kind of the way that carriage returns are represented in text and in websites sometimes. If we were to want to take this text and print it out somewhere nicely, we don't really want all those /n's, you know, to show up. So Doris, if you could scroll down a little bit past line 273 where we have the website text printed out, we'll get to the actual regex section, I think. Oh, okay, I'm sorry, my bad.
Yeah, this is
scroll up.
Yeah, this is the regex that
okay. I'm sorry. My fault. So yeah, so in line 267 through 269 is where we're going to actually do this regex work. So we're taking the web page variable as Doris just printed out for us, and then we're using the piping function that she explained. And in line 268, the first step that we're going to do is we're saying, okay, use the string replace all function, and we're going to find in the first part of the function there, the first parameter is all the stuff that we want to find. So we want to find all the /n's, and we also want to find all the /t's. That means tabs. So we're going to find all the new lines and all the tabs, and we're going to replace those with just a space. The reason why we're looking for /n, but we've listed /n is because // is actually a reserved character in a lot of different programming languages. And so what we need to do is we need to provide a second slash to tell the computer, yes, we really are looking for an actual slash. We're not just looking for n. And so if you're familiar with programming at all, you might be familiar with that escape character that you have to use. So after we found all the line breaks and the tabs, then we go through and we want to find all of the HTML tags. Those are those little carets there. So what we're doing here is we're using the gsub function, which is another way of kind of finding and replacing characters and strings. The first chunk of the parameters there is what we're actually looking for using regex. So we're looking for the opening caret and the closing caret. And then what the parentheses are telling us are we're looking for anything in between these parentheses. So it's kind of a grouping mechanism. It's not looking for parentheses. The parentheses are saying find me anything that's specified in between these parentheses. So what we're specifying with the period, the asterisk, and the question mark is pretty much anything. Where the period means find me anything. The asterisk, well, the asterisk is saying find me anything. The period is saying find me anything, any infinite number of times. And then the question mark, I'm kind of spacing on exactly what the question mark means right now, but I do have it in the Python script, so we can go back and I can specifically tell you what that means when we go back to the Python section. So essentially, if we run that chunk now, if you wouldn't mind, Doris, thanks. And then if we look at that, we can see now that all of our line breaks are gone, those /n's, all of our tabs are gone, the /t's, and then also all of the tags are gone as well. And so getting rid of the tags is something that can be really handy if you just want to get that text from the web page and you don't want any of the like web page type stuff in there. Okay, so Doris, if I could ask you to go ahead and switch to the Python section, we'll just look at those same exact steps when in Python. And yeah, if you could just comment those out. Okay, thanks. And then head over to that regex script. Yeah. Okay, so essentially, lines 10 through 21 essentially are things that we're already familiar with. We're importing the packages. Re is included with base Python, but you do have to import it. And then of course pandas, because we're going to read in some data. And then at the end of Doris's web scraping script, we saved off that website text file. So we're going to go ahead and read that back in so we can use that for our processing. Okay, so if you can scroll down a little bit, Doris, we're printing out that website text just to look and see what it looks like. In Python, on this section, the line breaks aren't showing up as /n, they're actually just showing up as /. So in line 32, what we're doing is we're specifying a variable called pattern. And we're using the regex compile function to say, okay, find any pattern that is a \space. Then in line 36, we're saying, okay, I want you to substitute using the .sub function on the pattern. I want you to find any instance of that pattern, and I want you to replace it with a blank string, which is the two quotes right next to each other. And the text that we're going to be looking at is website text. So what we've done here in line 36 and in line 36, we're actually printing that out, but then line 39 is where we're actually replacing the text that was in the website text variable with the new text that has all of those line breaks removed. And then in the next section here, lines 41 through 50, we're looking for the tags. So again, like I described before, our pattern is going to be tag pattern. And we can see we've got the two little carets there. And then here's where I specify out what the regex is actually doing. So in line 43, the carets are referring to the characters that designate the tags. Line 44, the parentheses capture everything within these parentheses. And then line 45, match to any character between 0 and unlimited number of times. Okay, and so at the end of that, what you're going to get is you're going to get the website text string that has all of those tags removed as well. Okay, and then Doris, could I ask you to highlight lines 52 through the end and then hit Command / to uncomment them. Or it's the yeah, there we go. Awesome, thanks. So I commented this out because it's actually kind of a different section. And before we run out of time, Doris, if I could ask you to scroll up to the top real quick. I just want to point out that in this script, I've listed lines 3 through 7 have some good regex practice sites. So if you open these up, you can put your text in the bottom and then experiment with your different regex expressions, and it will help you know if you are using them correctly or not. Okay, so if you could scroll down, Doris, and I'll just run through this text a little bit because it looks like some of the comments became uncommented as well. So the first thing we're doing here, this section just kind of tells you how you can read in some data from CSV and then work with the data frame a little bit using different regex patterns for different columns. So we're reading in some tabular data, which, let's see, Doris, if you could go up to the data folder, and there's the rpython regex.csv. There you go, you could click on that. And so this is just essentially a list of some universities, university locations in the St. Louis area. But we can see that there's some things that are kind of formatted very differently. We've got the city of St. Louis represented in several different ways: ST space Louis, ST period space Louis, STL, so on and so forth. We also have phone numbers that are formatted in different ways. We've got dashes there in line number 2. We've got dots in line number 3. We've got no spaces in line number 4, and so on and so forth. So the two regex items that we are going to work through in this section are going to be formatting that St. Louis city name and then formatting the phone numbers. So Doris, if I could ask you to go back to the script, and I'll just go through this script really quickly, and then we'll hop over to the R and I'll address the same thing in R. Thank you. Okay, thanks. So we bring in the data in line 56, and lines 58 through 66 are really just kind of looking at some different values. And it's okay, Doris, we don't need to print this stuff out for now. I'll just kind of walk through the code because some of my comments were uncommented, and I don't want you to have to spend the time to uncomment those. So in line 65 through 67, what we're doing is we're looking for the unique values of St. Louis City. Like I said before, there's about 86 different ways that you can refer to St. Louis if you ever start looking at data that people are inputting in. And so line 73 is the meat of what we're doing here. So we're saying, okay, let's make a pattern that is going to capture all of those different values of St. Louis. So the little caret says, find me everything that's at the beginning of the string. And then we've already seen that parentheses section before. That basically means find me anything. So this is saying find me anything that's at the beginning of a string that is followed by space Louis. So that's finding me my ST Louis and my ST period Louis. And then also we're using the or the pipe to represent or STL, because we know we also had some STLs in there as well. So that's finding my STL pattern. Then we're going to go through and we're going to find that pattern and we're going to replace it with ST period space Louis. That's happening in line 83. All right, and we're going to actually replace that, the original St. Louis with this new St. Louis. So now everything is all lined up. And then line 86 all the way down through 100 is basically just checking and printing out some of that stuff. Starting with line 107, we're going to do the formatting of our phone numbers. And so I'll just address the regex pattern here. So the first thing we do is we're going to take all of our values that are numbers, and we're going to get rid of any non-digits and any white space. So that's happening in line 116. So essentially that's taking out any spaces, any parentheses, any slashes, any dots, and it's smushing those numbers together. Then in line 128, we're going to divide them back out again. So we're going to say, okay, find me groups of 3 digits, 3 digits, and 4 digits. That's what's happening in line 128. So /D means find me any digit. And then the curly brackets means find me a group of 3 digits, a group of 3 digits, and then group of 4 digits. And so we find those groups of digits, and then we spit them back out in line 128 into the first group is going to be surrounded by parens. The second group is going to be itself. Then we're going to put a slash in between or a dash in between. And then you're going to give me that last group of 4 numbers there. So first group, second group, third group. And so when you run this script on your own, which I encourage you to do, you'll see that it's taken those numbers, it smushes them together, and then it parses them back out into the format you want, which can be really handy because phone numbers also come in a variety of different formats, especially if you're having people enter them themselves. Okay, Doris, so finally, home stretch here. If I could ask you to switch to our Studio Cloud, and we're going to be looking at the same thing. So in line 279, we're actually reading the data in. In 285 is where we're swapping out the St. Louis. So we're using the G sub function in R to do that, but we're using the same regex expression. We're still saying caret, give me everything at the beginning that is anything space Louis or STL. And then I want you to replace it with the second parameter, which is ST period space Louis, the way we want St. Louis to appear. And then what do we want you to focus on? We want you to focus on the data frame data, and then specifically the city column within that data frame. Then to do the phone numbers, then we are going to, again, we're going to find all of the non-digits and all of the white space in that phone number. So that's G sub, and then / capital D means non-digit, and capital or lowercase s means white space. So find me all the non-digits or white space, get rid of them. The second parameter is that blank string, so get rid of those. Specifically, I want you to do this in the data frame data, the column phone. Then in line 292 is where we're going to take those compressed numbers and we're going to separate them out into the groups. And that syntax is very similar to what we did in Python. We're finding a group of 3 digits, a group of 3 digits, and then a group of 4 digits. And then I want you to format them out as specified in that second parameter. So the first group is going to be surrounded in parentheses. The second group is going to be on its own, followed by a slash, and then the third group. And I want you to replace those in the data frame called data, specifically the column called phone. And then finally, after you get done parsing all of your data, scrubbing it, then you can output it to a data file called data scrubbed if you want to take a look at it, or maybe even put it in another package. Awesome, thanks Doris. So hopefully that looks better. We can see that our phone numbers look nice, our St. Louis looks nice, and so we've completed our data scrubbing. Okay, well, we actually made it through all of our code, albeit kind of rushed at the end. But on behalf of my co-hosts, I just wanted to thank you